Good morning and welcome to today's webinar. My name is Beth Capellis and I'm the Sales and Support Manager here at Triangle MicroWorks. Thanks for taking the time out and joining us. Today we'll be doing a recap of the IEC 61850 IOP testing event, preparation, testing, and results. Before we get started, I'd like to go over some housekeeping items while everyone is still joining. The webinar is scheduled to be 1 hour long. The audience is on mute, so please submit your questions online using the webinar toolbar under the section titled Questions. You can submit questions as soon as you have them. Please don't wait until the end. We will begin answering questions online as we have several engineers monitoring the questions and responding to them directly. We'll try to take a couple of breaks to read some of the submitted questions and are also happy to stay on after the webinar is over and answer as many questions as we can. With that, I'd like to introduce the folks behind the scenes answering the questions. Today we have with us Jim Coates, President of Triangle MicroWorks, and Eric Fabre, Senior QA Tester specializing in our SCADA Data Gateway, also with Triangle MicroWorks. Both Jim and Eric did attend the IOP. Next, I'd like to introduce our speakers. First, we have with us Christoph Brunner, President of IT for Power. Christoph is a well-known utility industry professional and 61850 expert with over 30 years of industry experience. Christoph has been involved in the development of the standard since the beginning. He is convener of Working Group 10 and member of Working Group 17, 18, and 19 of IEC TC57. He is an IEEE fellow and a member of several IEEE working groups, as well as a member of the PSRC main committee and the subcommittee H. Next, we have with us Jackson Moore, application engineer here at Triangle MicroWorks. Jackson received Bachelor's of Science degrees in both electrical engineering and computer engineering from North Carolina State University and has a background in power system engineering. Prior to joining Triangle, Jackson spent 5 years as a microgrid system engineer where he designed and developed local management control systems for multi-source microgrids. Currently, Jackson works with our customers and development team to understand and solve the challenges our clients face. Now that you know everybody, I'd like to give you a little bit of background on Triangle MicroWorks. We were established in 1994 and have over 28 years of communication protocol experience. We are headquartered in Raleigh, North Carolina, and have customers in over 70 countries. We work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market and greatly reduces their costs and development time. Licensing the source code library also includes support for your implementation and any issues that may arise in the field. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab or the field. They're designed to troubleshoot, simulate, and automate testing for both a single device or a complete substation. Lastly, we provide a SCADA data gateway supported on both Linux and Windows for protocol translation and data concentration with standard SCADA protocols, as well as OPC. It's available as software only or pre-installed on hardware. We are heavily involved in the standard committees that support SCADA protocols, like UCA Group for 61850 and DMP user and technical committees. Through our participation, we help define the protocols, stay up to date on the changes taking place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. Now that you know a little bit more about Triangle, I'd like to go ahead and hand it over to Christoph, who's going to kick off the webinar. Christoph, I'll go ahead and make you presenter.
Thank you, Beth. Okay, I hope you see now my screen with the presentation.
Yep.
Okay, welcome everybody from my side. So as an introduction, I will give a little overview on the IOP 24, in particular functional testing we did that. I will explain how we specified the requirements, and I will also summarize with a few lessons learned. For those of you that are new, and you may ask the question, what is an IOP? IOP stands for Interoperability Testing, and it has been organized by the UCA International User Group since 2011, where basically a group of vendors assemble with their products and test interoperability witnessed by witnesses, typically from users of the standard. This year we had the IOP in Birmingham, Alabama, and we had about 22 vendors of IDs and tools present, and about 125 people in total that were attending. You get an impression on the left side of the room where we were in. The testing we did this year included functional testing, but also secure routable goose testing, time synchronization testing, and some network configuration testing. When it comes to functional testing, we started basically in 2017 to do functional tests. Originally on the IOP, it was mainly focused on information exchange, communication, but in 2017, we started to do functional tests where we basically applied the products in a real kind environment. In the first step, we designed one large substation where every device had a predefined spot. The drawback of this approach was that when a device that was not ready for testing yet, because it had some issues, that impacted all the other devices in that bay, and because the device, one of the devices was not working. That's why for the IOP 24, we changed a little bit the scope and reduced mainly each test scenario to one bay with the devices that we would typically have in the bay, and additionally adding the devices that are needed in other bays, like an example for break effect protection. With that, participating vendor devices of a specific type, like a PIU, a process interface unit, or a bay control unit, could be swapped if you have troubles with one of the devices. In order to support the design, we wanted to have an accurate specification of the application requirements, including the signal flow. So we prepared that beforehand. On this slide, we see more or less the tests, the functional tests that we were planning to run. On the left side and on the right side, we see the single line that we had as a background. And we had basically the 4 different scenarios that we could test. We could test the line bay, we could test the transformer bay, we could test bus bar protection, and we could test the low voltage side consisting of incomer bay and feeder bay. And on these scenarios, we applied these applications. Not all of them apply to every scenario. Apparently, transformer differential protection only applied to the transformer bay, but that were basically the applications that we were using for our functional testing. In the test, there was, of course, the equipment that implemented the functionality that participated, like the IDs, protection and control devices, process interface units, or merging units. But then we also had a local HMI, and of course, there were also the clocks that we used to synchronize the process interface units for sample values. But in addition, we also had a couple of equipment that we used for test support, like a diagnostic tool that recorded detailed signals for analysis of the test results later on, test control that was able to interact with the devices in the test. As an example, change the mode from on to test. We needed goose publishers to simulate goose messages for testing, circuit breaker emulators, as we didn't have physical circuit breakers connected. And then, of course, the signal generators, the test sets that we use to inject analog or digital signals based on the test. Beforehand, we prepared the test specifications. They were prepared in 3 levels. The top level was the test scenarios, where we developed the scope for the functional tests based on the single line and the devices we need in a scope. The overview of the applications that can be tested for that scenario was also included there. Then we had a second document that described the test cases, characteristic of each of the test participants and test equipment, signal exchange related to the test case, and the different test steps. The main document that we used for testing was the test plan, we developed for each of the scenarios a detailed test plan. And there, each of the possible tests was described in details with preconditions, signals to capture for diagnostic purpose, test steps, and expected results. So that was mainly the document that we used to run the tests. Talking about the document test scenarios and tests. So that's an example for the test scenario that we had for the line bay. So we have all the devices included in the line bay that we need for the functions there. But then we also had some external devices, mainly the ones that receive the external trip in case of a breaker failure. So if the breaker failure here detected a failure, it was sending an external trip over to the transformer bay, which was then opening the breaker in the neighbor bay. So that's why we had, besides the core devices, additional devices in a test scenario as well. The tests that we specified did not only include tests in normal operation. For the line bay, the test in normal operation will be a control with synchro check and interlocking, protection trip and reclose, and breaker fail. But we also used various scenarios where we put as an example the LPU in virtual isolation. That means we put it in test mode, take them out of the system and perform the tests with the mechanisms in 6150 that we can use to test in a live environment. And again, then we run a couple of tests there, making sure that there was no influence from what was tested here to the rest of the system that was still in normal operation. The test plan, as mentioned, we basically generated one test plan for each test scenario, which was an Excel table that had one sheet per test. As an example, there was a sheet for the test controller, synchro check and interlocking. For each of the tests, it contained in a first part the specification of information that needed to be recorded by a diagnostic tool, settings to be checked, then steps to establish the precondition of the test, and then the test steps themselves. In addition, there was also a sheet in the test plan that captured the test participants, vendors and models of the devices and tools, as well as the witnesses, the persons that witnessed the test. In details, that looked like this. So that is an extract from a test where we list all the information we want to record. So we listed the data objects, data attributes that we wanted to have recorded in the diagnostic tool for later analysis. We then also started by checking the settings. In this case, which is from the line bay control and synchro check, we have the settings for the synchro check function that we could check if they were available in the data models according to 61850. Everywhere the witness could put in a pass or fail or not applicable if it was not there, and they could also add remarks on the test results. The next then was to start establish the preconditions. So as an example here, for the control and interlocking, we needed to have switch positions that we could simulate in order to stimulate blocking conditions from the interlocking. We needed to be sure that as a starting point, the breaker was closed. The signal generators on the line and on the bus simulated normal conditions. And then we also checked all the logical nodes LGOS and LSVS to be sure that the devices receive the relevant goose and sample value messages. On the right side, we show the signals that we could verify in the diagnostic tool as a result to check that these preconditions are met. And then after that, the key part was basically then the test steps. There were different test parts with the test steps. The parts for the control, as an example, would include open of the breaker, a deadline closing, a lifeline closing with synchronism conditions, without synchronism conditions, and so on, including also tests with interlocking conditions, whether it was blocking, and so on. For each of the test part, we had the steps that we had to do on our test tools, and then more or less the analysis on the diagnostic tool, what should have happened if the test was successful. So this test plan basically helped to go well prepared through the tests in a well prepared way, and had a detailed documentation as well of the test results. Another element we also planned, that was to do unit testing. It was planned before we start the IOP on the Sunday before, to do a unit testing of each of the devices in at least one configuration that it was assumed to use later. The unit testing basically included a verification of the configuration, compare the configuration in the device against what was expected from the SCD file, to be sure that the right configuration was loaded into the device, verification of the communication, like presence of goose streams, check the reception of goose streams in the LGOS, LSVS logical nodes, and also check that the reports are published and sent. Then also basic verification of the functionality. And last but not least, we also verified the behavior of the device when we applied test mode and reception of simulated streams, so that we could check that the device is also performing the virtual isolation elements as expected. If the device passed, then we could be pretty confident that it was ready for testing. Before the IOP, we also prepared the designs. So based on the feedback of device participation, so once we knew which devices, which vendors will participate with what kind of devices, we created what we called test groups for the scenarios with all the IDs. So as an example here, that was a test group for the line tests. So the IDs involved is the line protection unit, line bay control unit, the process interface unit, the bus merging unit that we needed for synchro check, and then for breaker failure transformer protection unit and the high voltage process interface unit. But we also defined the test equipment, so like analog signal generators, breaker emulators, but then also diagnostic tools, clock, HMI, and additional roles of the test tools. So all this was defined in the test group with the vendors and the models of the devices. And basically for the scenarios, we had 4 scenarios that we created for the line bay with the combinations of the vendors, 2 for the transformer base, 2 for the bus bar, and 2 for the low voltage, which included the incomer and feeder base. So a total of 10 scenarios were defined, and we also defined the SCD files beforehand to the IOP. Okay, so that was a little bit the content about what we did and what we prepared. Now I would like to talk a little bit about how we specified the requirements. For specifying the requirements, we use the concept of basic application profiles, which is the concept is defined in a technical report in the standard, and it basically does a selection and interpretation of the relevant parts of the standard for a specific application. A basic application profile not only specifies the data model, it also specifies signal flow between functions. Talking about application and functions, the concept of an application was introduced in one of the technical reports, 90-30, that is currently in the public, on the way to be published. An application basically uses typically multiple functions in order to be performed. As an example here, a breaker failure application starts with the function protection. When it trips, it initiates the breaker failure. We have the function breaker failure detection that supervises if the breaker opens. If it doesn't open, it needs to do a retrip, or it needs to send a trip to a neighbor breaker, and this goes through the function breaker interface. So basically, multiple functions work together to implement an application. A function itself can participate, of course, to multiple applications. The breaker interface function typically participates to many applications, like protection applications, control applications, among others. So that's a little bit the difference between an application and a function. Okay, so now when we started to prepare the IOP, we had selected these 6 applications that we wanted to test as part of the functional testing, and we started to create for each of them what we call a basic application profile. To give you an example, I used the circuit breaker fail. So each of the basic application profiles starts with a textual description how the functionality works. So it describes in words the basic functionality. And then it gets a little bit more formal. It has then a use case. So we describe the application as a use case with a use case diagram. So we have the protection as an actor that initiates the breaker failure function. So the breaker failure handling includes the use case failure detection. So it supervises the current and the position of the breaker, that the position opens and the current goes away. If this is not the case, then it has detected the failure and it will use the use case failure clearance to either do a retrip through the local breaker. For the IOP, we decided we don't do a retrip. So we only did an external trip to the neighbor breakers. And all the information was as well going to the diagnostic tool. So that's the way how the BAP is described in a use case diagram. The detailed behavior was then described with sequence diagrams. So here we have the example for a successful trip. So the current transformers sends currents to the breaker failure detection. The primary breaker sends the position. At a certain moment, the protection trips the breaker, and it also initiates the breaker failure detection. The start signal gets through, and the timer is started. And if the position opens and current goes away before the timer expires, this was a successful trip. That means the start becomes false. No action is required from the breaker fail. In a similar way, we also described the use case, the scenario for a failed breaker. So that was all described in details with all the interactions. Based on that, we then created the logical architecture of the application, where we have now again the protection as an actor, where the trip initiates the breaker fail detection function, which has a logical node RBRF. From here, we have a signal OpX in the case of an external trip that goes to a trip conditioning logical node. We have position from breaker interface coming in. We have currents from current interfaces going in, and we have trips going to the breaker that then opens the coils. So with that logic diagram, we can on one side nicely show the different logical nodes that we need, how they are embedded in functions, and as well the signals that are exchanged between these logical nodes. So as a result, we basically got then the detailed data model for each of the actors and the signal exchange, which was a very precise specification on how the devices had to operate. So based on these BAPs, we created beforehand a formal specification in the form of an SSD file based on the system configuration language. In that SSD file, we included the functions and sub-functions from the BAP. We also included single flow specified with source ref based on this technical report that is about to be published. In order to tell us how when the device implemented this function, they had to submit a spreadsheet in our process where they had to tell us how the logical nodes that were specified here mapped to the logical nodes available in the ICD file. They also had to tell us if they had deviations regarding the specified signal, if something was not supported or supported in a different way. And if the device supported later binding, that means the ICD file of the device provides already partially completed extracts, then they also had to tell us from the signal flow in the BAP which of the extracts we had to use for a specific signal flow. Okay, so that was the specification, and now I want to finalize with a few lessons learned. So during the preparation of the IOP, as part of the process to specify the BAP, we found a couple of areas where we identified that clarifications to the standard are needed. which basically will go into the working group 10 to get clarifications there. It was also assumed that the BAPs that we prepared for the IOP will be refined by the working group and may end up in a technical report. Lessons learned at the IOP. One of the lessons learned that, as I mentioned before, we asked the spreadsheet from the device vendors to fill in certain information. In the future, I think we should use a formal way there to specify device implementation specifics. The process ICD, as it is foreseen in the advanced engineering process based on the 90-30, would be a good starting point for that. The fact that we defined the test groups and the test schedule beforehand, that was also useful, as it allowed to prepare the SCD files before the IOP and have vendors verify that their devices could load the SCD files. Finally, the unit testing could only be done with some devices. One day was not enough, and mainly there was only basically one vendor there, one tool vendor there that did unit testing, so we couldn't test all of the devices. We focused on the ones for the first testing day, and I think it was positive because it took us less time to get the system up and running for the first tests, where we had most of the devices unit tested. Later in the week, we had some issues getting the devices ready. Sometimes that was probably because it dealt with new products and new functionalities. And of course, when we would have unit tested these devices, that would have been helpful. And of course, when we have conformance tested devices, so conformance testing of a device, of a product, is also important. Last but not least, I would mention that I think the IOP as such was very successful, and a lot of people that were there, I think, learned a lot. So I can only encourage, when you didn't yet attend at the IOP this year, that you consider to attend in the future. It can be with a device, with a product, but it can also be when you are a user as a witness. You can learn a lot, you have a lot of contacts that you get, and you see the latest developments. And with that, I would like to hand over back to Beth.
Thanks, Christoph. We did have one question come in. How can you get involved in the IOP?
Basically, we have an IOP every 2 years. The UCA Users Group announces them. If you are a member of a Users Group, then you should get the announcement directly. If not, you can follow on the UCA Users Group website. And then at a certain moment, there's time to register. Yeah, so basically everybody can participate, as I mentioned, either as a device vendor with a product or a tool vendor with a product, or if you are a user as a witness that is then witnessing these various tests.
Okay, great. Thanks, Christoph. With that, we're going to go ahead and hand it over to Jackson. Jackson, I'll make you presenter.
All right, thank you, Beth. All right, can you see my screen?
Yes.
Great. All right, so thank you, Christoph, for that excellent introduction. I'm now going to be talking a little bit more specifically about Triangle's involvement at the IOP. So starting out with planning and preparation. Our involvement process began during the planning and preparation phase, which Christoph already kind of gave us a good overview of earlier in this presentation. We were involved in the creation of the basic application profiles, or BAPs, but we also, as all vendors did, submitted our ICDs, or IED capability description files, for the various tools that we were going to be bringing, including DTM. I'll talk a little bit more about that in a moment, where we actually were emulating devices, or IEDs. So next we worked with a cross-company team, not even all just vendors, but also utilities, who worked together to help validate not just our ICD files, but every ICD file that was submitted by every vendor. And then we would notify the parties involved, whoever submitted that file, of any errors that were discovered. Ultimately, I think this led to a smoother integration process for power engineers, the team responsible for creating the SCD files. The validation was done using OCL, or Object Constraint Language Rules. These particular rules were written by a task force within Working Group 10 and applied using the open source RiseClip engine. RiseClips is incorporated into a couple different tools, one of which is our own SCL Navigator, which is a tool for both editing and creating ICD files, as well as other sorts of SCL files. So once these ICDs were submitted, one of the ones that we submitted anyway was used in DTM, as I mentioned, to emulate an IED that would participate in the functional tests that would happen later on in the week. Test Suite Pro was involved as a diagnostic and monitoring tool. Its role was to validate the performance of other IEDs during the functional tests and just ensure that they were operating as intended. To do this, we would collect goose messages as well as reports from all the devices participating in the test, and then compare those captured messages to the expected results. We also participated with our product SCADA Data Gateway, or SDG as we refer to it sometimes. So there's a defined role within the world of 62850 for a proxy gateway, and in one of the functional tests, we were assigned that role. And if you're not familiar with the term proxy gateway, I'll explain a little bit more of what that means here in a little bit. Lastly, we were part of the secure and routable goose tests that occurred here at the IOP. These tests assess the ability of both DTM functioning as an IED, as well as our client testing tool, Test Suite Pro, to both send and receive routable goose messages. The key being to ensure that these messages, which had security enabled, had authentication and encryption that could be authenticated and decrypted by other devices who were receiving them, and of course that our tools could do the same thing for messages sent by other vendors. So in summary, we participated in a lot of different areas, and we're really excited about this IOP and everything that was learned there. So now let's dive into one of our specific tools and one of the specific testing stages. So DTM, or Distributed Test Manager, and how it fit into the unit testing stage. So if you're not familiar with DTM, maybe some of you are very familiar on this call, but if you're not, it is a multi-protocol simulator. So it allows you to simulate devices in a variety of different protocols. Of course, at the 62850 IOP, we're focused on 62850 devices. So in this case, for unit testing, we would load in one of the SCD files. I believe there was 12 in total that were made over the course of the entire IOP, but we would load one in and simulate all devices that were defined within that SCD file. And you can see that over in the screenshot on the right. Now, for unit testing, we would disable one of those simulated or emulated devices in DTM. And then we would connect it via switch to an actual IED. The one that we had just disabled in our simulation mode, connected to the real physical one there on the network. And that would be our device under test. And we could validate both the system design and the functionality of that design under test. So for example, DTM might be used to simulate input signals, such as a trip condition, and then we could observe how the device under test responded. As Christoph mentioned, unit testing with DTM was not exhaustive. We were not able to do this for every SCD and not even for every IED. But it did help increase the level of confidence that we had for any given IED that it would be able to perform its job once we moved into the functional testing stage. And big shout out to the guys with Power Engineers and really everyone who helped work to make these SCDs files ahead of time. The fact that we had them ahead of time allowed us to prepare this in advance, pre-configured DTM to do this. And I'll walk you through a demo portion shortly that kind of shows how that worked. So moving on into the functional testing stage, I'd like to explain how DTMs kind of fit into this stage of the process. As I mentioned before, DTM was assigned to emulate different IEDs during different tests, specifically 6 different IEDs across the 12 different SCDs or system configuration descriptions, the different substations or bays of the substation that made up the functional tests. Additionally, aside from what we were actually assigned ahead of time, DTM was also able to act as an ad hoc emulator for devices that were unable to participate in the tests due to technical or logistical issues. For example, some devices were delayed in customs and never actually had a chance to arrive at the IOP. But we're really proud of the fact that DTM was able to quickly emulate these missing devices. So what does emulate mean in this context? Well, send any goose messages that that device was responsible for, subscribe to any that it needed to do its job, as well as subscribe to sample values, and then perhaps most importantly, replicate the functional behavior of that IED that was missing. Basically the same thing that we would do for the IEDs that we were assigned originally, but this just had to be done on the fly. We don't refer to this technology as necessarily a digital twin, but maybe a digital cousin. We're not looking to emulate the exact timing of the physical device, but instead just emulate the functional behavior. So on the right-hand side of this slide, you'll see a diagram illustrating one of the tests. At the top, you'll see the single line diagram specifically of the line bay. And below is a table detailing the various tests for the line bay. So these different boxes represent the different IEDs that would be required for maybe one particular test in this line bay. And DTM might be assigned to emulate one of these, say the bay control unit. But for example, if the switch control unit, sometimes these would be one device, the PIU, sometimes they'd be broken out into two. Let's say the SU is unavailable, then we could hop in and emulate that device's behavior as well, and allowing the test to continue in a situation where we otherwise may have had to abandon it. Down here at the bottom of the diagram, you see a long list of tests. It can look intimidating at first. Really what we're looking at is just 3 tests, these top 3 up here, and then we repeat those tests in different situations, effectively with different devices in virtual isolation. So with the LPHD sim flag set, so that device could respond to simulated messages from a test set, or even with the mode set to test or test blocked listed in these tests down here at the bottom. As I mentioned earlier, Triangle will also participate in the IOP with our product, the SCADA Data Gateway, or SDG. And SDG was assigned the role of a proxy gateway in one of these functional tests. If you're unfamiliar with the concept of a proxy gateway, don't be alarmed. It functions pretty similar to just a regular protocol gateway that you would see in a SCADA environment. But there are a couple key distinctions. One is that we're not translating protocols here. It is 62850 on both sides, specifically client server reports coming in and going out via the MMS protocol. And importantly, this is really the key distinction here, we maintain the semantic data model of the downstream IEDs when presenting the data to the upstream remote client. So let's take a look at this diagram below that explains this in a little bit more detail. On the left-hand side, we have several servers representing different IEDs that you might have within your substation. Via client-server communication, reports are issued up to a client that resides here within the gateway. Via internal mapping, that client will map the data that it receives via report to a proxy server that also resides within the gateway. Inside of that proxy server, I might have several logical devices, each representing the different servers that are downstream over here on the far left side, the different IEDs in the substation. I might have more nested logical devices inside. That's not really critical. What is important is at the lowest level, the data attributes contained within data objects, contained within logical nodes, all of that as it exists on the IEDs over here on the far left side is replicated in this proxy server and then served up via reports to a remote HMI, SCADA center, maintenance center, some offsite facility, typically offsite, and that's why you would use a gateway. I hope that kind of clarifies what a proxy server is. If not, feel free to ask questions in the chat, and we're going to answer those here in a little bit. We were also able to use SCG as kind of an ad hoc local HMI. By that I mean we could issue controls via the SCADA Data Gateway user interface. This is a product that runs on both Windows and Linux and has a browser-based UI. So you just log in and we could issue commands or controls down to the different IEDs to maybe operate switches, change an IED into test mode, so on and so forth, and then read that data back into the gateway. So moving along, the next tool we brought to the IOP, Test Suite Pro. So during unit testing, Test Suite Pro was connected to a single IED under test or device under test at a time. And we would follow a detailed unit testing script, some of which Christoph described earlier, and you can also see in the diagram here on the right. We use several features within Test Suite Pro to ensure that the device under test was properly configured. So for example, Christoph mentioned earlier, the model compare feature. This would allow us to verify that the device actually had the correct configuration, that the right or matching SCD file had been loaded in for the prescribed test. Next, we could test whether the tool, Test Suite Pro, was able to enable control blocks on the device, maybe subscribe to Goose messages and enable reports, and make sure that the data sets of those aligned with what we were expecting. We also assess the ability of the device to have its mode controlled and then see that reflected back on the IED's behavior. So for example, we might set the mode to test, read that back on behavior, and then check the quality of any data attributes being published from that device. Make sure that they have that quality set to test as well. We could use the Goose tracker to make sure that the device was in fact publishing Goose as expected, and then we could publish our own Goose using Test Suite Pro that particular device under test was configured to subscribe to. And then we could take a peek at the LGOS logical node. If you're not familiar, LGOS in 62850 is a method for an IED. It's a logical node on an IED that can tell you if it is in fact receiving the Goose stream that it's subscribed to. So since we only had a single device online at a time during unit testing, at first we would see that it was not receiving or subscribed. We could go ahead and turn on that Goose stream with the tool and then just check that logical node again, the LGOS logical node, and see that the device had in fact subscribed to that stream. And this could be done for both regular streams, and then once we started to test virtual isolation, we could do this with simulated as well. So I'm gonna go and take a moment and show you guys what that looks like in action. And to do that, I'll be using both DTM, which is what you see up on my screen now, and Test Suite Pro. So when we're actually at the IOP, I talked about what DTM's role was during unit testing. That's not exactly what you see now. In this case, I've simulated the entire substation by importing the SCD. We're really focused here in this particular test on the line bay, but I've disabled all of the devices in this simulation or emulation except for the LPU or line protection unit. So let's pretend that this is a real device that's sitting on the bench right next to me here, and I've got my computer connected to it. I would next switch over to Test Suite Pro. I've loaded in the same SCD file. So Test Suite Pro knows about all these devices and their IP addresses, and I'm now going to begin poking at the line protection unit or LPU. So I go ahead and connect to the device. And then as part of unit testing, kind of what was shown in that slide that I showed a moment ago, the first thing I would do is come over here and use the compare model tool. So I select the LPU, hit compare, and then what's actually happening in the background is Test Suite Pro goes out and pulls the device under test, in this case the LPU, and asks for a discovery. It tries to discover the data model on that device. So this is going to be a hierarchy. In this case, we're not showing child logical nodes as under their parent. We're really just showing it as a flat view, but we're showing, are there any discrepancies between the discovered data model that's reported from this device under test and what's defined in the SCD file. In this case, we see all green, a lot of the word match, which is great. It means that the correct SCD file has been loaded onto this device. Next, we can move down to the Goose tracker and see that our device is in fact publishing. So down where we see LPU right here, this is a stream that is being published by our device as well as this one. Where we see missing on wire in these other devices, that's just because I have those devices disabled in DTM and I'm not actually publishing from those. So again, all good. My device has the correct configuration loaded, as I can tell from the compare model, and it is publishing Goose as I expect. Now I want to see if it can subscribe to Goose that I'm publishing or that other devices are. So I move down to the LGOS matrix here within Test Suite Pro. If you're not familiar with this tool, it's basically a matrix that shows all of the Goose streams that are being published, shown here in the rows on the left-hand side, and then all of the IEDs that are subscribed to those streams. So in this case, since we're focused on the LPU right here in the middle, I can look at only this column. As I scroll down, I see that there is one Goose stream indicated right here by this red block that this LPU should be subscribed to. In red, as I hover over it, I see that indicates that I am not actually receiving that stream. Again, that's also reflected in this table over here on the right. So now I want to put the stream on the wire and see if my device is able to subscribe to it. To do that, I can just right click on the stream, say show in Goose Publisher, and then I'll just go ahead and begin publishing this stream. Because I don't have my device set into the simulation, the LPHD sim bit set. I'm going to turn off the simulate flags in the goose stream that I'm about to publish. If I come back up to LGOS, I see that flag has switched to green, indicating that the LPU is reporting, yep, I see it, I've got that stream, I can now respond to messages coming from that device. If I wanted to, I could go ahead and change the LPHD sim bit here and begin publishing goose streams that have the sim flag set and continue that testing as well. Instead, I'm going to move down to the mode behavior sim tool, and I'm going to go ahead and change the mode for this device. So again, the LPU is our device under test, and I'm going to go ahead and just change the mode on this parent logical device, and I'll change it to mode test. Go ahead and operate, update again to read back, and we see that my device has in fact swapped over to test mode, which is great. I see that reflected in the behavior. There's a variety of ways I could go and check the messages that are actually coming out of this device. For example, I could come down to the Goose viewer and look at the most recent messages that are coming out. And we can see, if I just highlight these last two, what's changed between these last two messages is just the quality. This last or second to last bit in the quality flag indicates that test mode is set. So we know that the device is functioning as expected. Once I changed the mode to test, it updated the quality, which is reflected out, as I said, in these goose streams. So with that kind of, it's a high level overview of the type of testing that we did when we were doing unit testing over at the IOP. So I'm going to go ahead and switch back to my presentation, and we'll talk a little bit about how Test Suite Pro was used in functional testing. Beth, if we have any recent questions that have come in, now could be a good time, or we can wait till the end.
We do have a couple of questions that came in, so let me go ahead and go down that list. Christoph, I believe this one is for you. You want to talk a little bit about the reasoning for the timing of the IOP being 2 years apart and kind of the activity that happens in between? A couple of questions came in asking about that.
Yes, so as we mentioned, we have typically the IOP every 2 years, and in between we may have virtual IOPs. Virtual IOPs are mainly focused on interactions between SL tools where we can verify these things. The reason why we have them only every 2 years is that it's quite a significant amount of efforts for preparation. I mean, we started typically the preparation a year before. All the specifications need to be written. Of course, we can reuse always from the previous year, but then it's also a huge effort in getting the material to the site, the peoples that are there, and typically for these peoples, that's a 7-day week, if not even more. I mean, this year we started setting up on Wednesday or Thursday. They started to set up the network. They were working through the weekend, so Saturday, Sunday, the vendors came and started to set up the devices. And then from Monday to Friday, we basically tested 12 hours a day. So we started at 8 in the morning and left at 8 in the evening. So it's quite a significant effort.
And when is the next IOP planned, virtual or in person?
It's not yet planned, but we will have a discussion at the end of this week, tomorrow, about lessons learned, and I think somewhere sooner or later we'll start planning the next one. I would expect the next virtual will be somewhere in the second half of 25, and then the next physical in 26.
Great. Next question, and I'll throw this out to both of you. What is the advantages of using a proxy server?
Well, yeah, so I'll take a stab at that, and Christoph, you can jump in as well if you have anything to add. So proxy server would be one half of the proxy gateway. So SDG or SCADA data gateway here, the proxy server would be this piece on the right-hand side. I would call the combination of the client and the server the proxy gateway. So you're preserving the semantic data model of the devices here on the far left side. And I guess, at least in my eyes, one of the differences, especially in a world where you're converting between protocols, everything's not just a generic point. So let's say I was going from 6150 on the left over to DNP or 104 on the right. I'm losing the semantics. I no longer know an xcbr.pos.stval is a double bit that indicates the position of a breaker. By the time it makes it over to the right-hand side, and I'm serving that data up to a remote HMI, if I've swapped protocols, then it's just going to be, you know, analog input 4 or something like that. And you would need a spreadsheet in order to know what that data point means. So because we're doing 61 and 50 all the way through, and because we're preserving the data model of the device, we're really saving that structure. And in some ways, it's almost transparent to the remote HMI. He does know that he's only talking to one server, but he sees the different logical devices here that represent all of the different IEDs in the substation. Christoph, do you have anything you'd want to add?
Yeah, maybe just to add on, I looked at the question a little bit from the perspective that we were wondering why we need that all. I mean, we have 650 communication down to the IED, we have 650 communication up. So I looked at it from the viewpoint, why do we need at all a gateway with a proxy server functionality in, and why can we not directly talk to the IEDs from the remote SCADA system? There, I think, if you look at it from that perspective, one of the reasons is just to have less associations required from the SCADA system down to the IEDs. We only have to associate to the proxy server instead of to all the individual IEDs. Then the other point is, in principle, we can remodel a little bit the data structure. So you can make a more device architecture neutral data model as well in the proxy server. That's a possibility, so that you don't necessarily reflect one-to-one the models from the devices. So that at the end of the day, when you look from the SCADA system into the substation, you have in each of the substations the same model, even if the device architecture is a little bit different within the substation. So that's one of the possibilities as well. And the third point I had, I'm just rereading what I had. Okay, also the third point, I think from an engineering perspective in SCL, if you would have direct communication to the substations with 61850, that would create like one huge SCL project, or at least you would need to have a lot of SCD files exchanged. So I think from an engineering perspective, it's also creating a certain separation. Having said that, it's not necessarily meant that there is not some discussions from some people going on that see that in the future we may not need that gateway and can talk directly there. Okay.
Okay, thanks guys. With that, I'm going to switch it back to you, Jackson. We've got about 7 minutes left to the hour. And we can stay on longer if need to, but just be conscious of the time.
Sure. Okay, so I'm going to go ahead and pivot back to Test Suite Pro, but talk about how it fit into functional testing. So I have defined several roles. You know, these included roles for devices like Christoph talked about earlier. So, you know, the BCU or the SCU, the LPU, the different IEDs that were protecting or controlling different pieces of the substation. It also defined roles for tools. So these included diagnostic or monitoring tools, local HMI, test device control, and even Goose Publisher. And Test Suite Pro was able to fill all these different roles at different times. But out of these, the one where I really feel like Test Suite Pro shone and what I'm most excited about is how it was able to perform as a diagnostic tool. Its main responsibility in this role was to monitor the functional tests in real time as they were actually happening, capture all the traffic that was going on. So this could be Goose messages back and forth between IEDs, as well as reports that were being published up to the client tools, specifically Test Suite Pro, and then visualize that. This allowed us to validate whether the devices in the functional tests were working as expected, and if not, we could identify where the issues were occurring, and in some cases, why as well. So as I mentioned, test results were captured and visualized using a variety of displays. Each one really has its own strength. The sequence of events log, I'll show you in just a moment. This was useful for recording both initial states and then state transitions for any data attribute that needed to be tracked for a given test. These test results could be reported or exported, to a CSV, You could also just use a screenshot, and it often served as the official record for tests in which Test Suite Pro was the primary diagnostic tool, and in some cases, even where it wasn't. The same data could be also analyzed using other tools like the Logic Analyzer, which provided kind of an oscilloscope-like view where you could compare and measure tight timings. Additionally, the signal flow diagram shown here on the right, this allowed us to visually depict data flow going between devices, and I'll be demoing that for you shortly. Finally, the Goose Viewer and Report Viewer served as reliable fallbacks. There, I kind of showed you that a moment ago when we were looking at the quality. We could capture all Goose traffic and reports that were going on the network at a given time. And if we didn't capture in one of the other areas, go ahead and check it there. So on the left-hand side, you see an excerpt of one of the test plans. And then on the right-hand side, you see some test results in Test Suite Pro, specifically from the sequence of events log. So this is a pretty basic test. This was actually from the transformer bay, and it was a differential fault. So we were really just setting up the fault, checking to see that the fault was picked up and that the breaker was tripped and then it stayed open. Really very simple. On the right-hand side, we see this is the device, or specifically the logical device that the data attribute was published from, a path to it, including the logical node, data object, and data attribute. And then up here, these ones that we see in white, in this value column, these would be the initial states. And then down here below, these ones that have swapped over to green, these are where a transition occurred. And then we have a variety of timestamps. Right here, I'm showing the receive timestamp. In the case of Goose, we could also look at the message header, and with reports, which commonly include the time data attribute, we could look at that as well to figure out kind of the order of events that things occurred. So, time for another quick demo. And to do this, I'm going to go ahead and switch back to DTM first, and then we'll show Test Suite Pro. So I've now enabled all devices in this simulation. And again, as I spoke about before, this is specifically for the line bay. The line bay does have a reclosing functionality on this breaker QA1 right here in the middle. And then we've rigged up this button here at the top to indicate a fault, specifically a distance protection fault. So when I click this button, a fault is actually going to occur. My breaker is going to trip open and then reclose. So if you looked, you might have seen the current disappear very quickly. That breaker popped to the left and then came back through. I'll go ahead and do it again. Oops, gotta click the right spot. There we go. Okay, so this was a simulation that we set up ahead of time, really partly for the purpose of validating the SCDs, but also used during the unit testing, as I talked about before, when we were testing with DTM. But now I want to kind of show you what it was like to sit there at the IOP and actually validate one of these tests. So for that, I'll switch back over to Test Suite Pro. I'll go ahead and connect to all my devices. And then I'm going to be using some of the displays that I spoke about earlier. Specifically, we'll start with the signal flow. So here, I'm just going to go ahead and start a capture. Actually, before I do that, let me just explain what we're looking at here. So the signal flow diagram, it's a way to visualize data flowing between IEDs, or in some cases, even internal to a single IED. So these gray boxes represent an IED, the darker blue, a logical device on that IED or device, and then these smallest ones are actually logical nodes that exist in the logical devices. So any line that's flowing between logical devices that's inside of one of these gray boxes, this is an internal signal that we're only able to capture via report, but we're able to make some inferences that this is how it actually operates. Whereas lines that are going between the box, these are documented in the SCD file. These are our Goose messages. So what we're going to see here in just a moment is the protection fault pickup. The PTRC, or the trip controller, is going to issue a trip that'll be received by both the recloser logical node as well as the breaker interface. The breaker will open, and then after a short time, the recloser will do its job and ask the breaker to close again. So I'll go ahead and begin capturing. So this is going to reach out and make sure it can subscribe to all of these Goose messages. And then I will come back over here to DTM. I'm going to just drag this off the screen and, oops, I clicked the wrong button. Well, let me monitor an SOE, all signals, and then hit that capture again. Okay, So now I'm going to trigger the fault. It happens very quick, as you can see, and I'll go ahead and stop, and then we can walk through it. So as I mentioned, the first thing that we see is the fault be detected. The trip is issued. The breaker opens. Again, this is the XCBR or breaker interface over there. If I hover over the line, then I can see that the initial value is on, indicating that it was closed. And then it transitioned to the off state, indicating that it was opened. If I continue to step forward, I see that the fault has disappeared, which is great. The breaker's open, so we hope to see that. We are no longer issuing a trip, which means that the recloser, after a short settling time, can go ahead and try and reclose the breaker. And finally, we see that happen as the breaker does close, and the recloser stops asking the breaker to close because it successfully has. So as I mentioned, we could view this data in several places, here on the signal flow, on the logic analyzer that I spoke about before, and then also over in the sequence of events log. Let me go ahead and pin this, and I will shrink this down and just walk you through what we see here. So it's really the same thing. Up here at the top, we see the initial states that I spoke about before, and then this is the test actually occurring. The trip picking up, right as the fault occurs, and then the breaker actually opening, so on and so forth. So we could use this as an official record for our test if we chose. And with that, I'm going to go ahead and pivot back to our presentation, where we'll talk about some lessons learned, as well as the last area that we participated in, which was Argoose. So if you're not familiar with Argoose, the R stands for routable goose, and it also applies to sample values as well. So routable means it can traverse a tiered network, and this is unlike traditional layer 2 goose or layer 2 sample values, where you're limited to a flat network unless you use something like a VPN to jump between networks, and even then you're really flat. So with the introduction of Argoose and RSV, routable sample values, there was a need for authentication and encryption. This has been introduced as well, and it's available in our source code libraries as well as our products. So 5 vendors, including Triangle MicroWorks, as well as PCI Tech, who makes Garibaldi, which is the KDC or key distribution server responsible for letting all of this work by distributing keys down to the other IEDs, participated at the IOP. It was a success, and it led to the first cross-vendor encrypted and authenticated goose message being sent and received. So Triangle participated with both DTM and Test Suite Pro, and we were able to receive cryptographic keys from Garibaldi, which is the key distribution server from PCI Tech, as well as send authenticated and encrypted routable goose messages. It was a pretty exciting time, and it was a lot of fun to be able to participate in that world first. Interoperability testing will continue for this specifically, with the different vendors involved agreeing to continue to test and kind of push this forward. It's really an area that we see the industry progressing, and we want to make sure that all the kinks are ironed out before this moves to become the world standard. So conclusions, just a couple things that I think bear repeating. At its core, IEC 61850, what is it? It's really, the only thing you can hold in your hand is maybe if you print out the collection of PDF documents. But these documents define a lot. At a bare minimum, they define 3 communication protocols, those being Goose, sample values, and the client-server communications that pass over MMS. A semantic data model, we always talk about logical devices, logical nodes, data objects, and attributes, as well as the engineering process that brings it all together. So anyone can go out and purchase these documents, implement them. I encourage you not to do that and instead purchase our source code library, but anyone can. And then in theory, everyone should be able to communicate and work nicely together. But how do we know that it actually works? So conformance testing is key, and it's definitely a big part of that answer, but it's not perfect. If you ever looked at a conformance test certificate for a device that has passed conformance testing, you'll note that it says the device has not been found or has not been shown to be non-conforming, because it's kind of impossible to say that a device is perfectly conformant. So at the end of the day, there's really just no substitution for going out and trying it, seeing if 2 devices that should be able to play nicely together actually can. And that's really what the spirit of the IOP is all about. It's really a lot of fun. It's an incredible atmosphere, kind of electric. Everyone is constantly collaborating, trying to get things done together. And I hope that next time each of you will consider going. As Christoph mentioned, it's not just for vendors, it's not just for people making tools or IEDs. There's a lot of participation from utilities and others who as witnesses. And with that, I'm going to go ahead and say thank you very much for your attention and turn it back over to Beth.
Great, thanks, Jackson. I'm gonna go ahead and take the screen back. I can see my screen. Okay, and with that, I'd like to thank everyone for attending our latest webinar, and just wrap up with a couple of final thoughts. If you are not already signed up for our newsletter, please go to our website, and there's just a quick form to fill out there to sign up for the newsletter, which will give you updates on our upcoming webinars, any training events that we have, any product releases. After you sign off of here, there is a 2-minute survey. It's only 5 questions. We'd really appreciate if you fill it out, give us some of your feedback. We'd love to hear from you. The recording of the webinar will be posted on our website in the next couple of days. Also, if you do fill out the survey, you will get a follow-up with a link to the recording. And then lastly, if you have any questions or comments, please feel free to email sales@trianglemicroworks.com. We'd love to hear from you. With that, we have covered all the questions. So again, thanks everyone, and we'll see you next time.